So another method of solving first order and first degree ordinary differential equation is the linear differential equation. So here are the standard forms. So if we're going to consider y as the dependent variable, so we have here the derivative of y with respect to x, and the second term contains a function of x multiplied to y, and the right side contains a pure x function only. Okay? Or if x is the dependent variable, then the second term contains a pure function of y multiplied to x, as in x only, and then the other side of the equation is containing a pure y function. So here are the corresponding integration factors. So for the first one, where y is the dependent variable, so it's e to the integral of p of x dx. And for the second one, it's p of y dy. And we're going to use that integrating factor in finding the general solution to the differential equation. We multiply the integrating factor with y, and it would be equated to the integral of the integrating factor multiplied to the one on the right side of the equation, your x function. Integrate it with respect to x, and then plus c. And for the second one, so replace y with x, and then the integrand would contain the pure y function. Integrate it with respect to y, and then add the constant of integration. For example, so let's try these three differential equations. For the first one, this is already arranged according to the standard form. So we have here derivative of y with respect to x, and then pure function of x multiplied to y, and the right side contains a function of x only. Okay, so the first step in finding the solution to the DE is to, of course, arrange first, and then once you have already written that in standard form, so identify the p of x and q of x. Okay, so this one would be the p of x, and then the right side of the equation would be the q of x. So next is to find the integrating factor. Okay, so find the integrating factor. Let's just shorten it using the letters I and F. Okay, so we'll use letter V just like in the other method, no, of solving first order and first degree differential equation, ordinary differential equation. So it would be e to the integral of p of x, since our dependent variable here is y, so it's p of x dx. And then so simply plug in the value of p of x, which is 2x plus 1 all over x dx. So the 2x plus 1 all over x is reduced to 2 plus 1 over x dx. So the integral is 2x plus ln of x. Or if we're going to separate 2x and ln of x using one of the laws of exponents, so it would be e to the 2x times e to the ln x, right? And then the next step is to already use the equation for finding the general solution, wherein we multiply the integrating factor with y, the dependent variable, and then equate it to the integral of the integrating factor multiplied to the function which is located on the right side of the equation. Okay, integrate it with respect to x, and then the constant of integration. Simply plug in the value of the integrating factor, which is e to the 2x, e to the ln x, and then for the right side, so the integral of e to the 2x, e to the ln x times, it's e to the negative 2x okay, dx, and then c. The purpose of separating 2x and ln x earlier is for this one, okay, so that e to the 2x and e to the negative 2x can be written as e to the 0 or 1. Basically, the right side, the right side of the equation is simply 1 times e to the ln x, which is basically just equal to x. Okay, so this is just equal to x. So it's x, okay, dx plus c, e the one on the left side. Okay, so integrating, it's x squared over 2 plus c. Then it's e to the 2x. And we write na lang e to the ln x plus x. Yes, it's x e to the 2x. Going to multiply the whole equation by 2, so that's 2x e to the 2x. And then if we are going to transfer squared to the other side, it's minus x squared, and the right side is c. Okay, so this is the solution, general solution to the given linear differential equation. So for the second example, we have here some trigonometric functions. So for the dx term, we have 3 terms versus the dy term, which has only 2 terms. So unlike in the first example, okay, so we need to really look into the functions here closely because this is not yet arranged according to standard form. So one technique is to look for the function that has a fewer number of terms and remove that function, multiply to a differential of y or differential of x, whatever is the case that is applicable, and divide that entire equation with that function. Okay, especially this is containing only 2 terms and it's pure x. So it would be better to divide the entire equation by 1 plus cosine x versus divide everything by a function which contains 3 terms, okay, times by the sine of x. So yeah, that's one technique. Depending on the given function, you can, of course, try, and if it does not transform into linear form, then maybe the dependent variable is the other variable, okay, y or x, case-to-case basis. So for this one, let's try dividing the entire equation by 1 plus cosine x, or if you're going to consider the negative sign here, okay, so it's negative of 1 plus cosine x. So our goal is to have the y as a dependent variable. So meaning we need to divide the entire equation also by dx so that it becomes derivative of y with respect to x. Okay, so arranging the terms, we get multiplying with 1 over negative 1 plus cosine x dx. So the first term would be dy dx, and then minus. Okay, so this entire expression, okay, from the given dE, the first expression, it's sine of x, okay, plus sine of x cosine of x minus y multiplied to sine of x, and then all over, okay, 1 plus cosine of x. Okay, so the negative sign here is already incorporated, okay, after multiplying it by 1 over negative of 1 plus cosine dx. So the right side is 0. Okay, So, dividing everything by 1 plus cosine x. So, another technique also, by the way, is to, aside from the number of terms, we have to consider the presence of pure x or pure y. Okay, so another hint is the presence of y here. So there's no term here containing x alone. Okay, so it's a trigo function. So look for the linear algebraic function. Okay, y. So meaning the second term in our DE in standard form is containing y and not x. Okay, so our goal here is to multiply this y with pure function of x. So we have here only this term, okay, divided by 1 plus cosine x, and the rest, okay, are to be transferred to the other side of the equation since they contain only. So the right side of the equation for a linear DE should contain only pure x or pure y if the x is the dependent variable. So ranging, okay, the terms. So distributing the negative sign here and here. So it's plus sine of x over 1 plus cosine of x. Is the pure x function multiplied to y. And then the right side is positive sine x plus sine of x cosine x. Okay, all over 1 plus cosine x, which is actually reducible. Okay, can be simplified further, okay, by factoring out sine of x. It's 1 plus cosine of x. We can divide the numerator by 1 plus cosine x, the common factor, resulting to sine of x on the right side of the equation. And we copy two terms. So we have here e of x, okay, multiplied to y, which is our basis later for getting the integrating factor. So for the integrating factor, so since y is our dependent variable, so same as the previous example, so it's e to the integral of p of x dx. Okay, so meaning sine of x over 1 plus cosine of x dx. So that means it's e to the, okay, using simple substitution, so we let u be equal to, okay, 1 plus cosine of x, and du would be negative sine of x dx. So we need a neutralizing factor, no, the negative 1. So it's negative of ln of 1 plus cosine of x, right? Okay, so this is our integrating factor. And for the general solution, so we multiply that integrating factor, okay, and y, and for the right side of the equation, integral of, okay, e to the ln of, or we can already simplify the exponential function, okay, so that we won't be writing stuff, no, in the general solution. So we can already simplify this. So this is e to the ln of 1 plus cosine x raised to the power of negative 1, okay, using one of the properties, no, of logarithm, or that means it's 1 plus cosine of x, okay, raised to the power of negative 1, okay, for integrating factor. We can write it as 1 over 1 plus cosine of x, okay. It's up to you. whichever is more convenient for you. Okay, so if we write it as it is, okay, with -1 exponent, so that's the integrating factor multiplied by y. And on the right side, so we have integral of 1 plus cosine of x raised to the power -1 times the right side, which is sine of x. Okay, and then dx, and then plus c. Continue integrating the right side of the equation. So we have basically sine of x all over 1 plus cosine of x. So similar to the one here in the integrating factor. Okay, so the integral is negative of ln of 1 plus cosine x, and then plus c. We're going to multiply everything by 1 plus cosine of x. Remove this expression here with the -1 exponent, which is not a requirement, depende sa agreement. Okay, so if we're going to remove that one with a negative sign, so we can write the solution as y is equal to negative of 1 plus cosine x. So you write the Lego function first before the logarithmic function so that you don't need to put many grouping symbols. That's the answer. So y equals negative of 1 plus cosine x times ln of 1 plus cosine x plus c. Or if we are going to write c only on the right side of the equations, we can transform the equation into y plus 1 plus cosine of x multiplied to ln of 1 plus cosine of x. Equals. So this is the general solution to the given differential equation. So in this example, we have x and t for our variables. So actually, this is also arranged already in standard form. So our pure function multiplied to the dependent variable x is 3 over t, pure function of t. And as we can see, the right side contains only t, okay, and no x. Therefore, it is a linear type of differential equation. So we go to the integrating factor solution. Okay, so this time the dependent variable is x. So our integrand here will contain the other variable, okay, which is t. So it's pure function of t multiplied, or integrand is pure function of t, and then integrate it with respect to t. Okay, so e to the integral of 3 over t, okay, and then dt. So that's e to the 3 ln of t, or ln of t cubed, okay, or simplifying it further, so it's t cubed, okay. So multiplying that to the dependent variable, which is x, okay, so the right side of the equation is integral of the integrating factor t cubed multiplied to the function located on the right side of the equation, 1 over t minus 2, and then integrate it with respect to t, and then plus the constant of integration. You already see the constant of integration here because the left side is the not in integral form. Okay. Of course, after getting the value of the integral here, so it's also a constant of integration, combining it with another constant of integration, still with a constant of integration. So We have here t cubed over t minus 2. Okay, we cannot use direct substitution, or rather simple substitution directly. Okay, so we need to divide t cubed by t minus 2 by long division or by syntactic division. So since the divisor is only t minus 2, so we can use syntactic division. So recalling how to use syntactic division is you write the numerical coefficients of all the terms with the terms properly arranged in decreasing exponent of the variable. So meaning start with t cubed and then followed by t squared, then t, and until the constant term. Okay. So from t cubed or dividend, so it's t cubed only. Okay, here it's t cubed only. So it's 1 for t cubed, 0 for t squared, 0 for t, and 0 for the constant term, and our divisor is t minus 2. So we solve for t, equate to t minus 2 to 0. So for t, it's the number to be written here. And then next step would be bring down the first number, multiply it to this, not to 2. So it's 2. Write it here, then add 0 and 2. So 2, and then do again the process 2 times 2, so which is 4, then 4, and then 8, and then 8. The result would be the first numerical coefficient is 4t squared. This is for t squared. Okay, then t, then the constant term, and this is the remainder. So, bale, t cubed over t minus 2. Not yet integrating. Okay, so here as t cubed times x, and then for the right side, so it's the integral of t squared, okay, plus 2t plus 4. For the remainder, we write it as 8 over the divisor, which is t minus 2. Okay, so integrate each term with respect to t. So we have here t cubed over 3, t squared plus 2t squared over 2, or t squared, and then 4t, and then for the last one, it's 8 ln of t minus 2, right? And then plus c. Multiplying everything by 3 and putting all terms except c on the side. So we have 3 t cubed x, okay, minus 3 t cubed, or rather t cubed only because it's t cubed over 3 multiplied by 3, so t cubed only is t cubed, and then minus 3 squared, put it on the left side, minus 12t, and then minus 24, okay, ln of t minus 2, and the right side. So this is the general solution to the given differential equation.